Hey, welcome to Data Skeptic, everybody, and our ongoing series on natural language processing. Very soon we're going to take a sub-focus on machine translation, going from one language to another. But before that, today's topic is on machine transcription, taking the recorded language like you're listening to here, and through a model arrived at via machine learning, translate those audio recordings into text. Measurements of the displacement of a diaphragm in a microphone, measured with great frequency, typically more than 44,000 times per second. Those amplitudes, a composite of all the frequencies being heard, stored on disk. Convert that audio data into textual data. Well, after all, human beings, we do that pretty naturally. You know, it wasn't that long ago when this was more or less science fiction. I remember the earliest times that I tried technology solutions, the various speech-to-text things that were available, and they were comically bad. Yes, I imagine even the youngest of you listeners is old enough to remember a time when there existed commercial products that produced something akin to gibberish when trying to solve this problem. Something so bad it wasn't even worth the effort of going back and fixing the few mistakes it had. It was all mistakes. But that sure has changed, and in a rather short period of time, really. Even still, machine transcription's far from perfect today. It's absolutely unarguably useful. We've passed that threshold. But are we at the finish line yet? Not sure. Probably not. Almost certainly not. But here's an interesting thought. If we look at the mistakes that machine transcription makes, are they going to be the same types of mistakes human beings make? If so, what does that tell us about the machine learning? If not, what does that tell us? I came across a great paper titled Comparing Human and Machine Errors in Conventional Speech Transcription. We get into the details of that in the interview today.
My name is Andreas Stolke. I'm a principal researcher with Microsoft. I work in the Speech and Dialogue Research Group, which is part of Microsoft's research division. I work on anything having to do with making use of speech and language in general for being understood by computers, for using computers in a more natural way.
That's an area of research that has, in my opinion, transformed rather profoundly in the last, decade or so. Can you tell me a little bit about your relationship to the field, maybe where you started and how you got where you are?
I was always interested in language. I did linguistics as an undergrad minor, and then when I started my PhD at Berkeley, I also did that as a minor subject. The way that people process speech is fascinating to me, or language in general. Language is such its own little microcosm of rules and behavior. So I'm a computer scientist. That's my major, but it was my major. But I'm just mainly interested in how we can make computers understand the way that people use language and speech and be understood by computers. And that's still what I'm doing now. I was initially at a company called SRI International right out of grad school. It's a contract research company. They do a lot of work with government funding, trying to push the technology forward on government money. I'm also affiliated with a research institute in Berkeley where I actually did my PhD, the International Computer Science Institute. And my day job these days is Microsoft, as I mentioned before.
Well, I read your recent paper comparing human and machine errors in conversational speech transcription, and was really glad to see some research along these lines taking place, because it's, I think, something that's, as we have these discussions about how systems are becoming now at, near, or sometimes exceeding human level performance, it's really important we have some understanding of the differences between the two approaches, if you will. Was that your core motivation in delving into this work?
Exactly. We had an R&D push, if you will, to try to reach human performance on a benchmark speech recognition task. And we worked on that for about 2 years, and I think we kind of declared success because we did reach a certain human level performance of word level accuracy in transcribing conversational speech. That's not to say that computers are all just as capable as humans in all respects. It's a very precisely defined and narrow task as far as speech recognition goes. But once you just compare the numbers, you immediately, as a scientist, you have to ask yourself, well, are there qualitative differences in how humans and machines perform? In other words, do we make different types of errors when we try to transcribe speech as opposed to machines? And so we did this little study where we tried to dig a little deeper into the results and try to tease out qualitative differences, as well as statistical correlations. For example, maybe the most important outcome of this work was to see whether the difficulty of transcribing one's speech, because we had multiple samples, we had multiple speakers that are data points in the measurement of transcription accuracy. How are they correlated? Are humans finding it hard to transcribe some speakers versus others in the same way that machines are? And we found a very, very strong correlation. So we found that basically, whichever speakers, either due to their accents or maybe the quality of the audio or other factors, were found hard to transcribe by humans, were also hard to transcribe by machines and vice versa.
Interesting. I'm wondering if we can maybe get into a formal definition of the task. What is the nature of the data set you begin with, and what do you hope to accomplish?
So this is a classic task called Switchboard. It's a corpus actually that was collected with government funding. Again, going back to those old days when DARPA sponsored pushing the technology forward back in the 80s and 90s. So it was a corpus of people communicating over the phone. They were recruited to talk on a certain subject. They got to choose from a list of subjects they felt comfortable engaging in some chit chat on, and they were paired up with other people who were interested in the same subjects, and then they held a phone conversation for about 10 minutes. And that was recorded, and back then it was actually recorded with analog devices, so on tapes, and then eventually it was digitized. These days that would all be digital. Then it was transcribed. It yielded a corpus of about 300 hours of speech by some hundreds of speakers. And that corpus was then used as a benchmark task for government-sponsored research to try to entice researchers to get more and more accurate in the speech recognition systems that they put together. Yeah, and so the task is essentially to do the most accurate word-for-word transcription possible. So we have a reference transcription that was created by another government-sponsored agency, the Linguistic Data Consortium at the University of Pennsylvania. So they did a multi-pass, very detailed transcription. That's our reference transcription, the words that the speakers spoke. And then you give that same audio to machine algorithms, and they spit out a transcription. And then you align these two transcriptions and you determine which words were recognized correctly, but also you count up the number of times that a word was incorrectly recognized. So some other word was recognized instead of the correct one, or a word was entirely omitted. We call those deletions. Or a word was recognized that wasn't actually there in the reference transcript. We call that an insertion. And you count up all the substitutions, deletions, and insertions, and you divide it by the total number of correct words, and that's your word error rate. And that's the benchmark metric that we're trying to measure ourselves against.
So when we say something is human level, like human level transcription, I don't know if I'm being arrogant here, but I feel like I take for granted that I'm a master of the English language and I can transcribe rather perfectly, but I suspect that's not the case. What does human level actually look like when measured?
Well, people are not perfect. And the reason is simply that to do our everyday tasks, we don't need to be perfect transcribers of speech. We can misrecognize little words here and there, especially the short words, like the so-called function words, like, the words that also tend to get misspelled maybe because they're so common and carry relatively little information by themselves. So when you have humans transcribe the same speech and then do the same kind of error rate computation, you end up with error rates right around 5%. That's again measured against the reference transcription, which was obtained with multiple transcription passes and very high levels of quality checking.
Makes sense, yeah. Do you have any, I don't know if there's a formal way to measure this, but any sense of how we might label or categorize that 5%? Is it, Some of it could be low quality recordings or accents as you managed, or maybe all of the above. What causes humans not to get 100%?
It could be all of the above. It could be poor audio. After all, these are phone conversations, so they have somewhat limited bandwidth. It could be just that someone's talking very fast, or they're munching on a sandwich, or there's any number of factors. Or it could be, yes, it could be an unfamiliar accent. We have people from all over the United States, so these are native speakers of American English, but they're from all different regions. So you have some strong Southern accents. You have all kinds of other regional accents in this data.
So when I think of, I've on occasions in my life struggled to understand an accent. I can definitely, relate to that, where I might have a reduced accuracy, just my background versus someone else who's heard other ways of speaking more commonly. But the machine that you're going to use for the transcription, presumably it had a wide corpus it could have been trained on. Now, maybe that corpus has some of its own bias, but what's the expectation going in? Do we think machines will have that same experience I described, that I know the things I'm used to hearing more, or does its vast corpora make it a little bit more robust in some way?
So this is in some sense an idealized speech recognition task, because in fact the training corpus is perfectly matched, almost exactly matched to the test data. The training data was set aside from the same data collection, from the same corpus. So they simply held out some of the data for test purposes, so you would never see it for training. That is, of course, never really true in real life. When companies like Microsoft or Google get the speech to transcribe that they do, it might come from a speaker or from a type of accent they've never seen before. So yes, the goal is to have the broadest possible coverage in your training data, and that's the only hope you have with current technology to do a good job on the test data.
Well, I'm eager to jump into the results, of course. That's what everyone's probably waiting for. But if we could keep them hanging for just a moment, I'm curious. Going into this, did you have an expectation? Did you think that machine errors were going to be fundamentally different in some way from human errors, or were you expecting to find them to be rather correlated?
I was surprised. I was expecting some kind of subtle difference in the types of errors that machines make, because has always been floating around this notion in the community, in this research community, that humans just bring to bear so much more world knowledge and background and contextual knowledge to the task, that whatever errors they would make would be, for example, such that the result would still make sense, so that maybe they recognize a word here or there incorrectly, but the overall utterance would still the recognized words would just be consistent and make sense, because that's what the human brain expects to recognize. And that, on the other hand, that computer algorithms, because they don't have the same vast background information, they would make sort of stupider errors, errors that are just render the whole utterance nonsensical some way, or just were sort of machine-like in some fashion. So I couldn't quite put my finger on what exactly that would result in terms of differences, but I did expect to find some kind of subtle differences in the way that humans and machines recognize speech, yes. And I was surprised.
Yeah, let's start diving into that surprise. Tell me a little bit about the results of your tests.
The first thing we did was what I briefly alluded to before, which is that we tried to look at the correlation of machine accuracy and human accuracy taken over the different data points, which are the different speakers in the test set. So we had some 30-odd speakers. There's actually two test sets, so it's a larger number, but we plotted the human error rate by speaker versus the machine error rate by speaker, and the data looked pretty strongly correlated. That means the data points, they cluster around a straight line. So in other words, the easy speakers for humans were also easy speakers for the machine, and vice versa. And what that tells you, while it doesn't tell you exactly what the underlying factors are, but it allows you to conclude that whichever factors and whichever aggregate effect the factors of difficulty have on the recognition task, they apply equally to humans and machines. That, of course, doesn't quite get us yet to subtle differences, because it's just a correlation of this overall word error rate, which I defined before. It's actually interesting to see that humans also have different error rates depending on the amount of effort that you put into it. We did an initial experiment at the outset of this project of trying to reach human accuracy by measuring human performance. So we simply gave our test conversations, the same audio that the computer would digest later, we gave those to human transcribers. Now you have to understand that Microsoft has a pipeline for transcribing hours and hours of speech that comes in through their speech-enabled services for various purposes, for training purposes, for quality assessment, and so forth. And so we simply gave this pre-existing test data to the same transcribers, and we didn't tell them anything special. We just figured, okay, we're going to use a professional transcription service and see what they can do with this old data. And we came out with an error rate of 5.9%, which is right around that level that I had mentioned previously. Okay, that was our one data point, but maybe they weren't doing a particularly good job. Maybe they could have done a better job had they known more about the task and maybe trained on it specifically prior to doing the test data. In fact, another group of researchers from IBM, they did exactly that. They actually teamed up with their transcription contractor, and they wrote a paper about it later. They had a larger number of transcribers, and they allowed themselves to actually pick the better transcribers for this task. And they also, that was a big difference actually, they allowed the transcribers to listen to entire conversations as opposed to isolated utterances. And they came up with a lower estimate for human error, which was 5.1%. And so what this shows you is that human effort matters when you try to achieve human accuracy. Mm-hmm. So the more effort you put in, the lower the word error rate will be. Not surprising, really.
And can we take for granted that the machine models don't exhibit the same fatigue behavior?
That is definitely one big advantage that machines have. They don't know fatigue. They can scale up the volume simply by devoting more compute resources to the task. That is correct.
Thanks to this week's sponsor, Brilliant.org. Every day, Brilliant publishes several daily problems that provide a quick and fascinating view into math, logic, science, engineering, or computer science. As an example, in the past month, tens of thousands of people have used computer science to effectively bake cheese biscuits. All right, what's that one about? Let me go to it. Okay, it's a resource allocation problem, and a really cute one at that. Easy to understand problem, a little theory, and you learn while you're having fun. Another popular daily problem from the past month was discover the extent to which elections can be biased by gerrymandering. Very contemporary topic. You can not only learn about it, but enjoy their interactive features that show the concept so you can try it yourself. Whether you're stuck in the commute or just want to learn something new every day, Brilliant's daily problems are fun, bite-sized ways to master concepts by applying them. Each problem comes with illustrations, animations, or interactive visualizations, and all the context you need to solve the problem yourself. If you like a good problem the way I do and you want to learn more, there's related courses that Brilliant offers that expand upon these ideas. So head over to brilliant.org/dataskeptics and finish your day just a little bit smarter. The first 200 of you that do so this week get 20% off the annual premium subscription. That way you can view all of the daily problems in the archives and unlock dozens of other problem-solving courses. Check it out at brilliant.org/dataskeptics. So the errors are correlated. Certainly, that tells me that the parts that are hard to transcribe are equally hard for machine and human. Are they making the same types of errors when they do make errors?
That was a second study we did on this data. So one way of looking at the differences is to actually look at the precise instances of error that occur. So we tabulated the word substitutions, insertions, and deletions that occur. So remember earlier I explained how you align the two word strings that you get for the reference and for the recognized words, and you figure out which words got either misrecognized or wrongly recognized, meaning inserted, or simply not recognized, meaning deleted. And you can tabulate the most frequent types of words, and you look at the sort of the top 10 list of each of these. And you do the same for the machine output, of course, and you find very, very strong overlap again. And maybe it's not a surprise in retrospect, but the short words, the very function words that occur very frequently in English, such as is than it in these very short words that also aren't very distinct acoustically because they are so short. Those get misrecognized most frequently. And if you look at the top 10 list for humans and machines, they are very similar. The ranking is slightly different, but the same types of short words occur. Again, maybe in retrospect, not a huge surprise because, again, the confusability of those words due to their short acoustic realization is probably a big factor here.
So if I were to, do a really poor version of my job and make a sensational, not very true headline out of this, I might say, new study finds that machines transcribe in precisely the same way the human brain does, since the behavioral outputs seem to be the same. What do you think about that? Are these methodologies working in the same manner that a neuroscientist might one day tell us the brain works, or are these just kind of coincidental artifacts in the data?
Well, I think you'd be jumping to conclusions there because obviously we don't know really how the brain works yet. The results might be similar, but that could be simply a function of the inherent properties of the underlying task, such as the need to discern the acoustic differences between words, between different pronunciations. And that's constrained by the acoustics and by the actual pronunciations that we all use, that the machine's trying to recognize as well as the humans. I think it would be more a function of the inherent difficulties of the task, as I mentioned before. And I should mention that we found one subtle but interesting difference in these top 10 lists of misrecognized words. There's a couple of different words, or you might call them sort of pseudo words, that occur in conversational speech that were actually confused by the machine more than by humans. And those are so-called filled pauses and back channels. Let me explain what those are. So filled pauses are basically the uhs and the ums that we use when we need to stall for time, when we're actually thinking while speaking and we need to indicate to our interlocutor that we need a little bit more time. They shouldn't jump in. We shouldn't assume that we're done speaking yet. I just need a little more time before I continue my utterance. So that's a filled pause. The most frequent forms in English are and. And then another special word or pseudo word that we find in conversation is a back channel, which could take, again, multiple forms. It could be something along those lines. Those basically tell the other person to keep talking. We're basically indicating that we're listening, that we're not trying to jump in at that location. The other person should keep talking. Notice how these are distinct. We have no problem distinguishing those. And if we did have problems, we would get into trouble because, in fact, they have a function as far as managing our conversation, the turn taking. One basically says, I want to keep talking. The other one says, you keep talking. Now, they are somewhat phonetically similar because they have the same, they have a vowel and the nasal in them. And in fact, the computer confuses them more frequently and much more frequently than humans. So this is one instance where we found where apparently humans are much more attuned to a particular word distinction that is maybe more warranted than just simply by their phonetic confusability. It's an actually pragmatically useful and important distinction that apparently humans learn to make very easily, or more easily at least, than the computer.
So we haven't talked in great detail about the underlying machine learning systems that you're studying around, basically, or the implementation of. Maybe that'd be a good topic for a whole separate episode. But just to get a high-level sense of this, can you mention a few details about the architecture of the system that essentially all of our discussion is somewhat conditioned on?
So we essentially put together the state-of-the-art techniques that people use at all the major research groups and industry research departments in speech recognition. And these are all based on neural networks. So we use neural networks, very deep neural networks with, tens of layers in the acoustic modeling, meaning in trying to model how an acoustic realization translates into a phone or a certain phonetic context. And then also the so-called language model, which basically is the predictive model that tells you what are likely or unlikely word sequences that you might hear. So the world knowledge, if you will, the background knowledge, the prior probability knowledge for speech recognition. That's what we call the language model. And that is also implemented as a neural model by having recurrent neural networks, basically going left to right or right to left, as the case may be. We do both, predict words based on their context. So it's an entirely artificial neural network based recognition system. We still use some traditional technology for finding the best hypothesis out of, thousands of possible hypotheses given a certain utterance. But so the decoding aspect of the system is still controlled by, finite state machines and a sort of technology that's been developed some decades ago. But the statistical modeling aspect is very much all based on neural networks.
What this research and your results tell us about the path forward for improvements to machine transcription?
Well, I think we are very careful in not making the claim that we've solved speech recognition. This is, as I mentioned before, is a very idealized and narrow task. It's useful because it's a benchmark task that is reproducible, and that's the whole point of doing research. You need a reproducible task. But in real life, the conditions under which speech recognition has to work they're much more broad and much more varied. And for example, a big issue still is the recognition of speech from a distance. So if you were in a conference room with multiple people talking over each other, and the microphone were in the middle of the table, people are seated around the room, you would have a much harder task recognizing speech. And in that type of scenario, humans are still much, much better at it than machines. It's a problem we're currently working on. So under these idealized conditions where you have the switchboard task, where you have people talking into a microphone that's close to their mouths, they're talking on a subject that is somewhat defined. It's not fixed because they can veer off the subject, but they're given a certain topic to talk about. And also the speakers don't know each other. So they talk in a fairly well-behaved way. They are polite to each other. They don't tend to not jump over each other when they take turns. All of those factors make the task somewhat easier than other speech recognition scenarios that you might find. I should also point out that there was a sort of companion task to the switchboard task, which is called Call Home. It's a different corpus where they had people talk over telephone again, but they were people who knew each other, so friends and family who had prior acquaintance, and they were not asked to talk about a particular subject. They just talked about whatever occurred in their daily lives. And on that task, the computer still was trailing behind human performance. Not by a huge amount, but there was definitely a difference there. So that tells you that the constraints that you put on the speech recognition task really are critical in determining levels of accuracy. And humans are just very much the champions when it comes to flexibility and adaptability to whatever task comes their way. There was one more experiment that we did, which was not as scientifically rigorous, but the most fun part of this paper, which was when we actually gave sort of a Turing test to speech researchers. We actually took the output of we had our test set, we had the machine recognition output, and we had the human transcription output for the same utterances. So we paired them up. We made a little interactive display where you would see the reference transcript, so what we believe to be the true words, and then we showed the errorful transcripts where some errors occurred both on the human side and on the machine side. And we displayed that for people at a speech conference. So most of the people who walked up to the system, they had some background in speech recognition or speech processing or in a technical field, so they were somewhat savvy, you would think, about technology. And we had them guess which one was the machine transcript and which one was the human transcript. And they performed basically a chance. It was an informal experiment. It wasn't carried out with the full rigor of, a psych experiment, but it basically confirmed for us that the types of errors that these two transcription systems make, the human and the machine, they are very, very close, not just quantitatively in terms of word error rate, but also qualitatively, because people actually found it very difficult to tell them apart.
Any insightful sort of ad hoc remarks from that group about, their thoughts, right or wrong, as to why, the machine made a certain error that a human did or didn't make?
Well, there were some gimmies that people who paid close attention, like, for example, once in a while there would be a typo, just a misspelled word in a transcript. And you would know that that came from a human transcriber because machines, they don't produce typos, they pick words from a predefined vocabulary, which presumably doesn't contain any. So that would be gimmies that the attentive test subject would easily identify as a human error. But that didn't really matter in the overall scheme of things. The performance was still indistinguishable from chance in a statistical sense. For a long time, when we studied not just speech recognition systems, but end-to-end systems, such as when a computer actually tries to understand a transaction or some task that you want to perform with speech input as the enabling modality, there was always this concern that maybe speech recognition isn't quite accurate enough yet so that the semantic, the action-oriented, or the dialogue component of the system would be doing a good enough job that humans would be willing to use the system. What this experiment shows us, I believe, is that we've now reached a level of performance with our speech recognition part of the technology that really shouldn't be a barrier anymore for the more understanding-oriented components of speech and language technology to do a good job. So it's no longer an excuse to say that speech recognition isn't accurate enough for people to be able to use natural language-based technology.
What's next for you in your research?
Well, of course, as I alluded to before, there are still other scenarios, such as the meeting recognition scenario. That's something that Microsoft is working on very hard, and other researchers too. There's many, many more difficult speech recognition scenarios where we are still hard at work to reach that human level of performance. The speech understanding component is another one where we still are not in any way close to human. And then there are other more subtle uses of language, such as detecting the frame of mind that someone's in, the emotional quality of an utterance. Those are all things that we're doing research on and that humans are very, very good at, and machines are not quite there yet.
Well, do you care to place any bets on when the tables may turn and we'll have another man versus machine experiment like this one to do?
I think these types of experiments will become more and more common. Already, some of my colleagues in machine translation, they have done a similar experiments where they were able to match, Chinese to English translation accuracy on a very narrow, well-defined task. So emotion recognition, similar experiments are being used. It's become quite common now to, in a research paper that talks about some new algorithm, to also at least reference or quote the human benchmark as a point that you want to compare yourself against. So I think it'll be a continuous effort to push technology further and further. Whether we'll ever reach machines, I'm skeptical about that, because human behavior is so complex and adaptable and surprising in many ways that maybe we don't even want machines to completely be able to duplicate that. As far as specific tasks are concerned, I'm certain that machines will get better and better at any single one of them.
Well, exciting times for sure. Andreas, thanks again so much for taking the time to come on and share all your insights and your work with us.
It's been my pleasure.